Okay, so question 5. The oxidation number and oxidation state, which is the same thing, of each element in the following 6 compounds. And then they give 6 different compounds. So first I'm just going to scroll down a bit and look at the rules that the junior tutor has written down. So when we determine the oxidation number of an atom in a compound, we usually follow these guidelines. Number 1, atoms have an oxidation number of 0 in their elemental state. 2, monatomic ions have an oxidation number equal to their charge. And then 3, in compounds, carbon is usually assigned an oxidation number of +4, but it can be 0 as well. Fluorine is usually assigned oxidation number of -1. Oxygen is usually assigned an oxidation number of -2, except when it is part of a peroxide, it would be -1. And in binary compounds with fluorine, where it is positive. And hydrogen is usually assigned an oxidation number of +1, except when it occurs as the hydride ion, under which case rule 2 wins. So in compounds, an oxidation number is given to all other atoms such that the sum of the numbers of oxidation on all atoms in the sample is equal to the charge on the molecule. Okay, so now let's put the rules into work. We have copper carbonate up first. So recall that oxygens typically have an oxidation number of -2. But since there are 3, then its total contribution of charge is -6. So I'm going to show just the contribution of all the oxygen atoms, but I'm going to circle -2, since when we report the oxidation number, we report it for a single atom. So the oxygen's oxidation number is -2. And then in the case of the carbon, one of the rules said it typically has an oxidation number of +4. So I'm just going to write that in, since it is likely to be +4. And now notice that we know carbon's oxidation number is +4 and oxygen's was -2 times 3. So if we added these charges together, we have -2. So if you see that the compound is neutral, then we need to neutralize the -2 that the carbons and the oxygens have taken place. So in the case of copper, it would have an oxidation number of +2, just to neutralize all the other oxidation numbers. Okay, so this is the answer for 5A. Now let's look at B. We just have methane. So in the case of typically yeah, I was wondering about this. So the carbon typically has an oxidation number of +4. But in the case of the hydrogens, hydrogen usually has an oxidation number of +1, like what they mentioned in the rules. But in order to neutralize the +4 from carbon's oxidation number, it makes sense if the hydrogen has an oxidation number of -1, and since there are 4 hydrogen atoms, then this balances out the carbon. Okay, so on to C. We have iodine and fluorine bonded together. So fluorine usually has an oxidation number of -1. So the iodine will have +1. Okay, so now let's look at D. We have CH2Cl2. So in the case of chlorine, its oxidation number is -1. So I'm going to circle that in green. But again, since there are 2 chlorine atoms, I'm going to multiply this by 2 just to show the overall charge is -2. In the case of hydrogen, typically has an oxidation number of +1. But again, there are 2 hydrogen atoms, so I'm going to multiply this by 2, and you get +2. So now you'll see that the hydrogens and the chlorines cancel each other out. So that means the oxidation number of our carbon would just be 0. Okay, on to E. We have sulfur dioxide. So again, oxygen typically has an oxidation number of -2. I'm going to circle that. There are 2 atoms of oxygen, so overall it gives off a -4 charge. And to balance this out, 1 sulfur atom should be +4. And then lastly, we have Nh4 Ammonium Chromate. Okay, so this example is a little more tricky, but it's easier if we were to separate them into their ions. In the case of Nh4, this is the same thing as writing its single ion. And then let's do the same thing for the chromate. Which has a charge of 2-. Okay, so let's do the ammonium first. So if we recall that hydrogen tends to have a +1 oxidation number, since there are 4 atoms, then overall they give off a +4 charge. So I'm going to circle +1 since this is the answer for the hydrogen. And since the ammonium ion has an overall +1 charge, that means the oxidation number for nitrogen should only be -3. So this gives us an overall +1 charge for the Nh4 ion. Okay, so now let's do the same thing for the chromate. Oxygen typically has an oxidation number of -2. So I'm going to circle that in green. But there are 4 oxygen atoms. So let's multiply this by 4. And it gives off an overall -8 charge. So if we want our chromate ion to have an overall -2 charge, then that means that the chromium should have an oxidation state of +6. Okay, so now let's see what the junior tutor said. In determining the oxidation number of an atom in a compound, we usually follow these guidelines. Number 1, atoms have an oxidation number of 0 in their elemental state. 2, monoatomic ions have an oxidation number equal to their charge. 3, in compounds, carbon is usually assigned an oxidation number +4, but it can be 0 as well. Fluorine is assigned an oxidation of... Oh yeah, I read this part already. But yeah, this is just a reminder. So again, there are some instances where some of the compounds might have exceptions. So that's why it can get a little bit tricky, but you kind of get the hang of it the more you practice finding oxidation numbers. So here's what the answers say. For letter A, copper carbonate, overall charge is 0, so they have oxygen having a -2 oxidation number. Carbon is +4, copper was +2. CH4 was kind of confusing to me as well, since hydrogens usually have a +1, but I just said that if carbon had a +4 oxidation state, then the hydrogen should be -1 if the overall molecule is neutral. So I'll just take note of that at the end there. -1 for fluorine, iodine +1, hydrogen +1, fluorine -1, carbon in this case would be 0. Oxygen is -2, sulfur's +4. And then they separated the last compound into their individual ions and got +1 for hydrogen, -3 for nitrogen, -8 for oxygen, and then +6 for chromium. Yep, so this solution is correct. Okay, so I just added my bit.